This is the lecture for chapter 7.1. Have your note sheets ready so we can get down the important information for this section. We're going to be looking at properties of the normal distribution, which means we're going to be solving probability problems using equations and graphs. And we're going to look at two different types of graph. One's called a uniform probability distribution, and another would be called the normal curve, which is what we've been kind of studying. And so all this leads to us solving probability problems using something called a probability density function. Sounds really complex. All it is, it's an equation used to compute probabilities for continuous random variables. And so this is different than chapter 6, which was discrete random variables. And so we have a slightly different situation here. So let's go ahead and take a look at an example of what we're going to be talking about here. And like the other section, we'll be using StatCrunch to do the calculation. So we won't be using the formula. We won't be plugging in ourselves. StatCrunch will be using the equation. So our first example is called uniform probability distribution. In the term, important term here is uniform, meaning the same. Everything's the same. So we have a situation where the probability is the same regardless of the value of the variable. And so let's take a look at what we're talking about here. Let's assume the UPS, United Postal Parcel Service, is supposed to deliver a package to your front door, and the arrival time is somewhere between 10 and 11. So we'll let the random variable x represent the time from 10, the time from 10 when the delivery is supposed to take place. So the delivery could be at 10 a.m., which means x equals 0, or at 11 at x equals 60. With all 1-minute intervals of time between 0 and 60, equally likely. And there's the important term in terms of this being uniform. That is to say, your package is just as likely to arrive between 10:15 and 10:16 as it is between 10:40 and 10:41. We don't know. We just know that's equally likely to arrive at any time between 10 and 11. The random variable x can be any value from the interval 0 to 60, because any two intervals of equal length between 0 and 60 inclusive are equally likely. The random variable x is said to follow a uniform probability distribution. We'll answer some questions now, but that's the idea, that we have these equally likely outcomes within this time interval, and so there's a uniform distribution. What would that look like to us? There's a graph on your note sheets there. This is what it would look like. The probability has the same value between 0 and 60, and this height represents the probability. And so let's take a look at that. Let's go ahead and define what we had talked about before. And so an important term that we need to remember, it's something called a PDF, not like your files, but it's called the probability density function. And again, this is used with continuous random variables. Where did we say that? Right here. This is important. This is when we use this one compared to chapter 6, which was discrete. It's important to maybe remember that in chapter 6 we use discrete. So take a minute to remember what that means. Retrieve that from your memory. What does that mean? Discrete random variables. That was chapter 6. Now we're in chapter 7. We're going to be looking at continuous random variables. And so a probability density function is an equation used to compute probabilities. It must satisfy the following properties. And so there's some properties here. Property 1, property 2, the total area underneath the graph of the equation that we'll give it to you. The total area must be equal to 1. Which is, again, connected to the idea of 100%. We're talking about probabilities. And then the shape of the graph of the equation must be, and what I was saying, the shape, or really what we're interested in the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random x. So when we make the graph, the heights have to be greater than 0. And so this is the idea of a probability density function. Let's take a look at our first simple example. And so in this case here, we know that the area under the graph of the density function over an interval represents the probability of observing a value. This is an important idea now. We're going to be using this term area, which is going to be the space underneath the graph. And really, what we're talking about is that area. When we're using this term area, we're really referring to the idea of probability. And so we use areas to determine the probability. And we don't calculate areas with formulas. We do, but we use StatCrunch to get that. And so, for example, what is the probability that the package will be delivered between 10:15 and 10:30, right? That the X value is between, that the package comes between 10:15 and 10:30. We're using the same situation. And so our variable X on the X-axis goes from 0 to 60. And what we're concerned about, what is the probability that it will come between here? Now, 160, this is our probability here on this side. Where does that value come from? Well, we know the total area underneath the curve. The total area has to equal 1. And then since we know this here is from 0 to 60 is 60, this has to be 160, because 60 times 160 equals 1. So this total area, the total area equals 1. And so to answer this question, what is the probability? We're really capturing what is this area right here. And so what's the distance from here to here? It's 15. This height is 1/60th. So what we're really doing is finding an area of a rectangle. Base is 15. The height is 160. So the area in this case here is going to be length times width, or base times height, 15 times 160. And so then that equals 15 over 60. And so that turns out to be, I think, 1/4. 15, 5, 3, 12, 1/4. So the probability here would equal to 0.25 or 1/4. There's a 25% chance that the package will come between 10:15 and 10:30. And so that's the idea of a probability density function as it relates to uniform density function. And before we finish this, I think it's good to kind of maybe walk you through the PowerPoint real fast so you can see that it move. We talked about probability density function. Here is the uniform density function for the situation that we talked about. Again, the uniform, it's a straight line graph here. And so we had that down because the probability is the same that the package would arrive at any time during 10 and 11. We have the random variable x, which is the time, how many minutes after. Values of the random variable x less than 0 or greater than 60 are impossible. So the function only has a value between 0 and 60 because we're only looking at that 1 hour interval. We know the area under the graph. This was the important idea I had you write in. The area under the graph of a density function represents the probability. There's an explicit connection, direct connection between calculating area and the probability. And this is what we actually were calculating, probability. And we saw that this was 15 here, this was 1/60th, and so then you got that area of 25. And so that's what we were talking about.